In section 8.3, we're going to be talking about rational functions and their graphs. And I apologize in advance for how long this video is going to be. If a function has a polynomial in its denominator, its graph has a gap at each zero of the polynomial. And there's a couple different situations that could happen here. A rational function also is a function that you could write in the form f of x equals polynomial p of x over polynomial q of x. Now, here are the different situations where you could possibly have a gap at each zero of a polynomial. So first, you could have a situation like this where you don't really have any gaps or holes, and we'll talk about why that is in a second. You could have something like this where you have a hole in the graph where it looks like a continuous line, but then all of a sudden there's just one random spot that's not there. And kind of what we've been talking about before, where you have asymptotes. So you have kind of lines that serve as like barriers to the graph. So in that first graph there, the reason that we don't see any holes in the graph here is that there's no value of x that can make the denominator be 0. And as you look in the denominator there, x squared, no matter what I plug in, even if it's a negative value, is always going to spit out something positive. So any positive or non-zero number plus 1, like I'm always going to have at least 1 in the denominator. I would call something like this a continuous graph. A continuous graph has no jumps, breaks, or holes. And one way that you could think about it is you could draw that graph with your pencil, and your pencil would never leave the piece of paper. In this next example, we have something that we would call a hole in the graph. Here we have the function y equals x plus 3 times x plus 2 over x plus 2. In my denominator, you could see that my x value cannot be negative 2. Negative 2 would make that whole function be undefined, which is why I see that hole. Another situation is where I have an asymptote. Here I have the example of y equals x plus 4 over x minus 2. And as I could see there, my x value cannot be 2, because if I plug 2 in for x, that would make the function undefined. Both of these graphs would fall under the category of a discontinuous graph. And again, discontinuous graphs will have like jumps, holes, or breaks. And what we're going to focus on here is holes in a graph or like an asymptote in a graph. And these all fall under the category of points of discontinuity. If a is a real number for which the denominator of a rational function f of x is 0, then a is not in the domain of f of x. We've talked about that before. F of x is not continuous at x equals a, and the function would then have a point of discontinuity at x equals a. And that first example that we looked at, where we had the hole in the graph, I would say that that function has removable discontinuity at x equals negative 2. Because if you look at that function, the hole in the graph is called a removable discontinuity because you could make the function continuous by simplifying it. So if I cross out those x plus 2 terms and redefined that function as y equals x plus 3, now I would have a point at x equals negative 2. That point would be f of negative 2 equals 1. Again, that would be removable discontinuity because I could make that graph, or I could redefine it or simplify it to where that discontinuity would go away, aka y makes it removable. In that other situation, y equals x plus 4 over x minus 2, I call that non-removable discontinuity because there's no way that I could simplify or redefine that function at 2 to make it a continuous function. And then that's a situation where I would have like an asymptote. So in our first example here, what is the domain and points of discontinuity of each of the following rational functions? Are they removable or non-removable? And finally, what are the x and y intercepts? In this first function, we have y equals x plus 3 over x squared minus 4x plus 3. Now, I might look at that denominator and think, oh, okay, that's a quadratic function. I might be able to factor it. Two numbers that multiply to give me 3 and add up to give me negative 4. I could rewrite this to be x minus 1, x minus 3. Even with that, though, nothing's going to cancel out on the top and bottom. Although now that I did kind of rewrite that in factored form, I could see that my domain is all real numbers except x equals 1 and x equals 3. My points of discontinuity would be also at x equals 1 and x equals 3. They're non-removable points of discontinuity because I can't simplify them out of the equation. Finally, my x-intercept is going to be when my whole function equals 0, or to put it more simply, when the numerator is 0. That might be an easier way to look at it. So to make my numerator 0, that would be when x would be negative 3, so that's my x-intercept. Finally, my y-intercepts is when x equals 0. So all I would do here is plug in 0 wherever I see an x, type that all in my calculator, or just do it in my head. I have a y-intercept at 1. In this next function, we have y equals x minus 5 all over x squared plus 1. Now, I can't factor the numerator or the denominator because, again, I have x squared plus 1. Nothing's going to simplify there, so my domain here is all real numbers. Also, it's all real numbers because, again, this is a situation where there's no value that I could plug in for x that would make the denominator be 0. So, again, every number is going to work here. My domain is all real numbers. I have no discontinuities. My x-intercept, again, would be when the numerator equals 0. So that would be when x equals 5. And my y-intercept, again, I plug in 0 for x. And I would get a y-intercept at y equals negative 5. Let's look at one more example. Here I have y equals x squared minus 3x minus 4 all over x minus 4. Here, again, I look at that numerator and I think, oh, okay, cool, I can factor this. I could rewrite that numerator as x minus 4 times x plus 1. And now looking at that, I see that I have things that are going to cancel out on the top and bottom. So I'm going to keep that in mind as I go through my points of discontinuity. My domain here is all real numbers except for x equals 4. X equals 4 is my point of discontinuity, but I can cancel these out and redefine this function as y equals x plus 1. So since the function can be redefined or simplified, that point of discontinuity is removable. My x-intercept would be where at x equals negative 1. My y-intercept would be at 1. So finally, let's talk about how to find vertical and horizontal asymptotes. Vertical asymptotes of rational functions. The graph of the rational function f of x equals p of x over q of x has a vertical asymptote at each real zero of q of x if p of x and q of x have no common zeros. This sounds more complicated than it's actually going to be. If p of x and q of x have x minus a to the n power and x minus a to the n power as factors, respectively, and m is less than n, then f of x also has a vertical asymptote at x equals a. Now, I would write this all down, but when we look at an example, these are actually going to be pretty simple to find. What are the vertical asymptotes for y equals x plus 1 all over x minus 2 times x minus 3? Again, I'm looking to see, okay, what I have in the denominator, if it doesn't cancel out, then it's going to be an asymptote. So 2 and 3 are zeros of the denominator. Neither is a 0 of the numerator, so it's going to stay there, it doesn't cancel. So x equals 2 and x equals 3 are vertical asymptotes, and that's it. Finally, horizontal asymptotes are where I have a couple different situations. How I find a horizontal asymptote is I have to compare the degree of the numerator to the degree of my denominator in each function. If the degree of the numerator is less than the degree of the denominator, my horizontal asymptote is always going to be y equals 0. That's also the x-axis if you want to make a note of that. If my degree of the numerator is greater than the degree of the denominator, I won't have a horizontal asymptote. Finally, if my degree of the numerator and denominator are the same on the top and bottom, my horizontal asymptote would be at y equals a over b, where a is the coefficient of the term of the numerator of the greatest or leading degree, and b would be the coefficient in the denominator of the leading term with the greatest degree. So let's look at some examples here of how to find horizontal asymptotes. Here I have y equals 2x over x minus 3. In this example, my degree of the numerator and denominator are the same. They're both 1. So what I'm going to do is compare the highest degree coefficient of the top and bottom. In this case, it would be 2 and 1. So my horizontal asymptote is y equals 2 over 1, or just 2. In my next example, I have y equals x minus 2 all over x squared minus 2x minus 3. My degree of the numerator is less than the degree of the denominator because I have the first degree over the second degree. So without even doing any other math here, I know that my horizontal asymptote has to be at y equals 0. Finally, if I look at something like this, y equals x squared over 2x minus 5, my degree of the numerator is higher than the degree of the denominator, so I don't have a horizontal asymptote in this situation. To end this video, finally, let's put this all together and graph a function using the information that we have. I want to sketch a graph of y equals x squared plus x minus 12 all over x squared minus 4. So looking at that to start here, we'll just start with the horizontal asymptotes because we just did those. My degree is the same on the top and bottom, so now I have to compare the leading coefficient of my numerator and denominator. So my horizontal asymptote would be 1 over 1, or just 1. So what I'm actually going to do here is I'm going to plot my asymptotes and key points like x and y intercepts, and then kind of connect the dots and make my graph from there. So I know I'm going to have a horizontal asymptote at y equals 1, so I sketch that out. Next, let's try to find vertical asymptotes. I could rewrite this function in factored form as y equals x plus 4 times x minus 3 all over x plus 2 times x minus 2. Looking at that in factored form, I can see here that I have to have vertical asymptotes at -2 and +2 because those are zeros of my denominator and they don't cancel out with any zeros on top. So here are my vertical asymptotes. Now that I have those barriers, I can start to plug in some key features to be able to sketch my graph. I have x-intercepts when my numerator is 0. So that would be at x equals -4 and x equals 3. So on the x-axis, I have points at -4 and +3. So I graph those so I can kind of see where I'm at in terms of the asymptotes. Finally, to find my y-intercept, I plug in 0 for x, and I know that I have a y-intercept at +3. And the cool thing that I could do from here is that I know that these figures can't cross over any asymptotes. So I can just kind of sketch my graph from there. And it's going to look super weird, like a bunch of squiggly lines. But this is what my graph would look like. And I'd finally be done.